So now we have the other consequence of the rank nullity theorem, which is sort of the mirror image or flip side version of the non-injectivity we talked about. And so this is for non-surjectivity now. So suppose now we're mapping into a larger space. So suppose the dimension of V is strictly smaller than the dimension of W. All right. If we take a linear map then from the smaller space into the larger, then there's no way that it can be surjective. And so the idea for the proof is very similar to the one that we just saw. And so that is, if we take such a linear map, then we use the equation from the rank nullity theorem and solve this time for the rank. Then the rank is going to look like the dimension of V minus the nullity of T. So that's by the rank nullity theorem. And then since the nullity is non-negative, the smallest it can be is 0, right? That can only be smaller than the dimension of V. And then we're assuming that the dimension of V is strictly less than the dimension of W. All right, and so now since the dimension of the range of T is strictly less than the dimension of W, it must be the case that it cannot be all of W. And that's it. Okay, and so also, just like the previous one that we were looking at, the idea that you should have in mind is best understood in terms of finite sets. So to be surjective, a function needs to be going from a set with at least as many points in the domain as in the codomain, or there's no way that it can be surjective, right? And so here we're looking at vector spaces, so there's an infinite number of elements of each vector space. But if we talk about bases instead and spanning sets, then it reduces to questions about finite sets because we're looking at finite dimensional vector spaces. So in order to be surjective, T must map a basis of V to a spanning set for W. All right. And again, the idea that you should have in mind is that if you've got a basis of, say, a two-dimensional space, and you're mapping it to a space that needs at least 3 elements to have a spanning set, right? So some three-dimensional W, then no matter how you decide to map V1 and V2, there's always going to be at least one thing that doesn't get covered. So there's no way for this to be surjective. Okay, and so then we have also an immediate corollary for the non-surjectivity theorem, again in terms of systems of linear equations. This time we'll take the inequality reduced, or reversed, so that n is strictly less than m. And we'll look at inhomogeneous systems and the solvability of inhomogeneous systems. So if the number of variables is strictly less than the number of equations, then an inhomogeneous system typically has no solutions. And so again, the system that I'm looking at here is A11x1 plus summed up to A1 n xn. And this time, since it's inhomogeneous, we'll put a B1 here. We have to do inhomogeneous because we know that for homogeneous systems, they're always solvable because you always have the trivial solution. But the idea is that for inhomogeneous, you could pick a B that doesn't work. Okay, and so here's a diagram to explain why it's not necessarily going to work. So if we have, say, some two-dimensional space like this, so here's a picture of F2, and say we have some injective linear map T. Well, if it's injective, then the output of this is going to look like a plane as well. But if we're mapping into R3, then maybe that plane looks like this. And then there's going to be an entire complementary summand that we're not reaching. So it's going to look something like this. So back here when I said typically, another word that's often used here is generically. What I mean is that most of the time, so for any choice of B out here floating in space, there will be no solution. There will only be a solution if I happen to pick a point that's in the plane, right? And so if I have chosen, say, so if I've got B equal to, and I choose my first two coordinates, and I'm choosing these at random, there's exactly one choice that will allow me to solve that system. If I choose anything else, the system will not be able to be solved. So in general, there's no solution. There's only going to be a solution if you make that very, very special, almost contrived choice. So that's what I mean by typically. It actually has a specific meaning. It means it occurs with probability 0. So, and again, we're going to prove it by exactly the same means. We will convert this into a question about linear maps because that's what we have information about. And we will define the linear map in exactly the same way that we did before. So the first argument of the output is going to be the equation that we have on the left side set equal to B1 on the right side. All the way through until the one where we have it set equal to xm on the right side. Okay. Then T is not surjective by 324. So there's elements of the codomain for which the equation Tx equals B has no solutions, cannot be solved.